So why we needed this? So this theory, because one of the, as you can see, the picture says it all. Valence bond theory was not able to explain why it is this is attracted by the this is liquid oxygen which is trapped between two magnets. So clearly it shows magnetic property. It is attracted by the magnets, and so it must have some unpaired electrons. But valence bond theory may, you have pairing of there was pairing happening, which we have discussed earlier lot many times. So that was one of the major glaring faults that was lying in that previous theory, and we discussed how new theory was developed. And so, in the scheme of new things, so this is what we understood, that oxygen, if you are going to make diatomic molecule of all the elements in the periodic table, this is the diagram that fits all of them, oxygen onwards. But for certain lighter elements, we discuss the scheme. So this you must be because we had several classes in offline mode. You must be able to explain why a sigma bond is having lower energy, why a pi bond is having slightly higher energy. All these aspects very well you should be able to explain. If you follow my previous lectures, you must you can do that. Okay, locate the nucleus, locate the electron density, consider the constructive and destructive interference, and then explain what is happening. Look at the internuclear region, internuclear axis, and everything is clear. Okay, so and then we discussed further how why the diatomic molecules of what is that, the lighter elements, lighter than oxygen, elements which are lighter than oxygen, behave differently. And in that context, I first, no, this one, yeah. This is what we discussed in the last few previous classes. Some board work was also done on this. So it was, if you look at this S and P energies, 2p and 2s, as the nuclear charge increases, energy of both of them decreases along the period as you move along the period. But if you are looking at this thing up to here, I mean, so at hydrogen, when we start with hydrogen, both are 2s and 2p are at the same place, but slowly the energy becomes hydrogen helium. So this is the case of hydrogen helium. Uh, And then, so this is just an extrapolation. If I have to imagine what could have been the nature of graph if we start with hydrogen, then it ऐसा कुछ होगा. हाइड्रोजन में आपका 2s 2p का एनर्जी सेम है, ये भी हमने पहले डिस्कस किया हुआ है, you know that. And as the nuclear when it is becomes multi-electronic system, there's shielding penetration effect that comes in due to electron-electron interaction, repulsion. And so the energy even within the same shell between two different orbitals will be different. जब तक एक इलेक्ट्रॉन है तब तक वो सेम रहेगा, इसीलिए हाइड्रोजन में आप 3s 3p 3d have same energies, 2s 2p have same energies. और उसके बाद धीरे धीरे gradually as the you increase the number of protons in the nucleus, there's attraction between it attracts the one electron, the electron strongly, and so both the energies goes down. And as you already know, so one thing is that conceptually you have to visualize it. Formula comes later, formula बाद में आएगा, ठीक है ना. कभी भी आप ये ध्यान रखिए, उसको पहले concept, you need to understand the concept first. Then when you have asked about the how to quantify that thing which is happening, then comes the mathematics. तो पहले तो ये कि you are increasing the number of electrons, number of protons at the center. So all the orbitals which we are considering as one electron wave function, they will be drawn inwards. Okay? So the energy will be because of increased attraction from the increasing nuclear charge, the protons. The, the attraction is felt by both of them, but greater, the 2s orbital which is closer to the nucleus feels that effect much strongly. And therefore, there is a greater decrease in the energy of 2s orbital as compared to 2p. And so, this kind of profile is obtained. Now, in the lighter elements, less from lithium to nitrogen that we were going to discuss, here we can see that there is the orbitals are still very close to each other, the 2s and 2p. And so mixing can happen when they are similar or, in terms of energy, very close to each other. In that case, mixing has been observed when they are higher than this. In case of oxygen or fluorine, the 2s 2p levels are much farther apart in terms of energy. So वहाँ पे फिर ये मिक्सिंग नहीं होता. मिक्सिंग अब होता कैसे है, इसको हमने दो स्टेप में समझा. फर्स्ट थिंग, द नॉर्मल केस, ऑक्सीजन ऑनवर्ड्स जो हमने एक जनरल स्कीम बनाया, वो स्कीम अभी भी वैलिड है, ठीक है. एंड वी स्टार्ट विद दिस, एंड बिकॉज एंड देन वी कंसिडर दिस interaction of these orbitals of similar symmetry, which is so first to consider it that this is the sorry it's the first one, yeah. So after this basic scheme has been obtained, we started with this sigma 2s sigma 2pz both lying along the internuclear axis, and so these can further interact, which we, so this is what second order interaction of the MOs, molecular orbitals, which are lying, which are having the electron density right, having electron densities along internuclear axis. ये सिर्फ उन्हीं ऑर्बिटल्स के बीच में होगा. Only those orbitals which are having electron densities along internuclear axis, ठीक है. So रिकॉर्डिंग इज हो रहा है. सो सेकेंड ऑर्डर इंटरेक्शन इन सब के बीच में ही होगा. सो पहला इंटरेक्शन जो हम कंसिडर कर रहे हैं, सो व्हेनेवर यू आर लुकिंग एट द इंटरेक्शन ऑफ ऑर्बिटल्स, यू हैव टू कंसिडर. ऑनलाइन वाले सुन पा रहे हैं? हेलो, ओके गुड, ठीक है ठीक है. थैंक यू फॉर द इनपुट. यस सर. हाँ ठीक है, चलिए. तो आप लोग जल्दी आ जाइए बस, वी आर मिसिंग यू. ठीक है, हाँ देखिए बाकी लोग क्लास में हैं यहाँ. सो ये सब हमारे पहले के क्लासेस में डिस्कस किया गया था. सो वी आर लुकिंग एट द सिमिट्रीज एंड देन कंबाइनिंग इट, राइट. sigma 2s sigma 2pz, these are the orbitals which are closer in energy. They also have right kind of symmetry, so they can have the interaction. They can so again it will be in the same pattern, constructive. So one orbital will be formed which will be through by the constructive interference of the two orbitals, and another one with destructive interference. So energy of one will be shot up, it will go up, energy of the other will go down. ठीक है. So constructive interference 2s plus 2pz, 2p minus 2s, sigma 2p minus sigma 2s. तो इस तरह से ये वाला लेवल जो है ऊपर चला गया. आपका ये पार्ट तो एक्सप्लेन हो गया, ठीक है. जो बहुत सारी बुक्स में ड्राइंग होती है, बहुत वेरी क्लियर नहीं होता है, ये जस्ट आप रट लेते हैं. लेकिन हाँ, अब यहाँ पे ये आपको क्लियर हो गया कि ये चीज़ ड्यू टू द डिस्ट्रक्टिव इंटरफेरेंस ऑफ दीज टू ऑर्बिटल्स, द रिजल्टेंट वुड बी समथिंग विच इज हैविंग हायर एनर्जी, ठीक है. Another one due to the constructive interference of the two, there will be one new molecular orbital form which is will be having lower energy. ठीक है। इसी तरह से so you can also see that the orbital pi 2s 2px 2py which doesn't have electron density along the internuclear axis unaffected, that remains unaffected. So this remains unaffected because as I have already said that only for those orbitals which are having electron density along the internuclear axis, so this will remain unaffected. तो ये कहना गलत होता है अक्सर, people make the mistake here, they say that pi की ऑर्बिटल कम हो गई है, pi ऑर्बिटल की एनर्जी कम नहीं हुई है, वो जैसा पहले विदाउट कंसिडरिंग दैट वन जो होता है वैसा ही है. It is just that it is having a second order interaction, and sigma 2p, one of the orbitals created, is having slightly higher energy here. So that equivalent वो yellow dot जो यहाँ पे बॉक्स दिख रहा था वो अब यहाँ है. ठीक है. So yeah, so this is, so next we consider the other two orbitals, the sigma 2s and sigma 2s star. मतलब जो एंटी बॉन्डिंग ऑर्बिटल्स हैं उनका भी सिमिट्री ऐसा है कि दे कैन have overlap, and then another two set of two orbitals will be formed, one here and another one having lower energy. So constructive and destructive interference. So this is the final, so now you combine all these together, you have the final picture of looking, which appears like this: sigma 2s 2p. So now you see the orbital diagram becomes slightly asymmetric. Asymmetric in what sense? Now you understand much better. This one going down, इससे भी नीचे है ना, ये वाला और हाँ ये वाला भी कंस्ट्रक्टिव इंटरफेरेंस वाला है, तो इसके कंपैरिजन में ये थोड़ा सा उससे थोड़ा सा नीचे. ठीक है ना. Pi orbital remains the same, no change. This one is going up, and anti-bonding combination, combination of two molecular orbitals which were earlier formed as a first order interaction. So in this manner you can so this aspect is clear, which is also illustrated through this diagram: pi 2p remaining the same from 2s. So this is lithium beryllium Li2 Ve2 up to O2 and F2. So you can see 5 orbitals having no change in energy, but it is the energy of the sigma combinations that changes from here to here. So it is so it comes down to these two things. So basically you are having 2s and 2pz, because z orbitally p का जो पाई बनेगा दो x और y होगा, वो तो इंटरेक्ट नहीं कर रहा है, सेकेंड ऑर्डर इंटरेक्शन. सो देयर इज नो मिक्सिंग ऑफ दैट. So this is only mixing of 2s and 2pz orbitals which we are seeing through this scheme. And the reasons, so you have to look for the symmetry whenever you are combining the orbitals, and for the energy, if they are similar in energy, overlap is better. And this we had discussed earlier. Yeah, something so like that. So yeah, the example was that one for hydrogen and fluorine. When you try to combine them together, you look for orbitals from the symmetry point of view. फ्लोरीन में कौन कौन से ऑर्बिटल हैं जो हाइड्रोजन के 1s के साथ कंबाइन कर सकते हैं? 2s सिमेट्री के हिसाब से तो 2s भी सूट कर रहा है. दिस इज 2s, ये 2s वाली लाइन है और ये 2p वाली लाइन है. एनर्जी, हाउ द एनर्जी वेरीज, जो अभी हम वहां पे देख रहे थे. आप देखिए कुछ देर पहले ही अभी हमने देखा था 2s और 2p का वेरिएशन कैसे होता है लिथियम से. ठीक है, एटॉमिक ऑर्बिटल्स, it is almost the same curve. Okay, it is just another thing that hydrogen 1s भी यहाँ पे इंक्लूड किया गया है इधर, ये सब. ठीक है. सो when we look at this structure, सिमिट्री के पॉइंट ऑफ व्यू से दोनों ही सुटेबल है. But when we look at the energies, second consideration is the energy, then we find that these two are differing much more. Minus 36, minus 40, जबकि ये minus 18. So it is, so the if one is combines with this 2p orbital, the overlap will be better, it is, will be more effective, so the stability, the orbital form will be more stable. So so because of this energy difference that we have discussed, 1s and 2s do not combine. 2s energy remains like this, no change in energy of the 2s of fluorine. The energy of 1s here and 2p, 2p का अभी हमने देखा, 2p is having slightly more negative energy, so it is drawn slightly lower than this, and the difference in energy between minus 13 minus 18 is less. So this is what we show as the combination of sigma and sigma star. Again, the other two orbitals, px and py, remain, they do not have any other counterpart in hydrogen to interact, तो फिर वो it is again remains as non-bonding. ठीक है, when the energy remains unchanged as compared to atomic state, we say it is non-bonding, right? So इस तरह से HF का डायग्राम आपका बन जाता है, और this was for carbon monoxide, and इसमें you have, yeah, so again only those orbitals. So ध्यान दीजिएगा, पाई ऑर्बिटल में हम मिक्सिंग वाली ये डॉटेड लाइन जो दिखा रहे हैं, दिस इज फॉर मिक्सिंग ऑफ ऑर्बिटल्स एंड ऑल दैट, वी नेवर शो टू दैट फॉर पाई. पाई के साथ कभी मत कीजिए, डू नॉट शो इट विथ पाई, द मिक्सिंग इज नॉट हैपनिंग फॉर द पाई ऑर्बिटल, राइट? So always be careful about that. Okay, so this orbital has a contribution from, so यहाँ पे क्या बात है, एनर्जी ऑफ द 2pz ऑर्बिटल ऑफ ऑक्सीजन, ऑक्सीजन का p ऑर्बिटल, it is lying having intermediate energy between 2p of carbon and 2s of carbon, so it can combine with both. Okay, so when you try to combine, so इसको हम दो स्टेप में अगर तोड़ के we try to uh, uh, dissect it into and show it in two steps, and it can be understood. First, let's consider that only 2s and 2p of the oxygen is combined. In that case, you will get bonding and one anti-bonding set. Now in the other next step, you can think of only combining the 2p with 2p of carbon. Okay, carbon. So the effect is this, and then when you take all of them together, combining both of them together gives you this, which is having almost the energy similar to this 2p oxygen. Okay, so this is, that's why it is treated as a, there is negligible change in the energy of this orbital, which is a combination of this and these two giving rise to orbitals. So you are creating three orbitals. One, this is bonding, MO, anti-bonding, MO, and this is the non-bonding. Non-bonding तो लिखा हुआ है. So this is how you generate this kind of diagram, which so the diagram that is shown over here is a result of, if we break it down into smaller steps, this is the how it happens. Okay, when all the mixing are considered, three orbitals will be there, and that's how we consider this thing. So these pictures, so when you are looking at the carbon monoxide, the two orbitals, the अच्छा हाँ, okay, ये हमने क्या किया था, yeah, so normally if the two combining orbitals are of the same type, pi, if you are looking at how the pi orbital would have been formed, this is the picture. So this is like uh, CC double bond अगर हम कहें for the moment let's consider, या फिर something, हाँ. So in this case, if double bond is formed, then it is something like this. Both the atoms have equal electronegativities, so there will be equally distributed electron clouds, symmetrical distribution of the electron densities in the molecular orbital. But look at this picture. Now, when one is carbon, another one is oxygen. So oxygen is more electronegative, has the p orbital is much lower in energy. So when you are making diagram like A, B, I told you, when you make orbitals and so if this kind of situation arises when the two combining orbitals are different, having different significantly different electronegativity, in that case the contribution to the sigma should I generalize it, I should say bonding MO, not sigma, and anything, it could be whether it is pi overlap or sigma overlap, bonding molecular orbital will have greater contribution from this contribution, that is, so it is almost like it is having and to this is the anti-bonding MO, which is having greater contribution from A, right, greater contribution from this. So the anti-bonding orbital will be having uh, greater contribution from the less electronegative element, मोर इलेक्ट्रोनेगेटिव एलिमेंट जिसका कि ऑर्बिटल नीचे है, मोर इलेक्ट्रोनेगेटिव मतलब उसका इफेक्टिव न्यूक्लियर चार्ज ज़्यादा है, ऑर्बिटल्स are drawn inward, they are having lower energy, and that's why you are drawing it here, lower position, right? Electronegative में आप why you draw like this? So once you understand this, अब this same picture this is to be conveyed through diagram of the how the orbital overlap occurs. ये तो एनर्जी लेवल डायग्राम था, ठीक है, जिसको कि आपने तो ऐसा कुछ होगा. Greater contribution comes from b orbital. B atom means the electron, there is greater electron density of this orbital lying on the p as compared to this one. So when we are having C and O, oxygen is more electronegative, so the bonding MO will have more electron densities towards oxygen. So that's why you see this. In this case, it was symmetrical when the two atoms were same, and which is changing to asymmetric form, showing you are able to show greater electron density on oxygen, less electron density on carbon for this. If you are looking at the other orbital, the anti-bonding one, ये वाला, तो ये पहले ऐसा सिमेट्रिक होता है, इसका ट्रांसफॉर्मेशन देखिए. So I am trying to show the transformation A to B, है ना, कि we should be, अब ये ऑनलाइन वाले मिस करेंगे, जैसे कि मतलब हम ये दिखाना चाह रहे हैं जब इक्वल था, दो चीजें थी, ये bonding MO and this was seen by the same one, ठीक है, and then these two atoms are significantly different. So इस केस में जो आप ऑर्बिटल बना रहे हैं, so this one is having, so this is a picture for the orbital bonding demo, ये वाला, this you are looking at this. So आप अपनी कॉपी में अपने हिसाब से इसे ड्रा करके डालना. So this one corresponds to this combination that we have equal, and both atoms are having equal energy. So ये सारा drawing जो हमने इसको लिखा है. And then and so for this bonding and anti-bonding, ये सब anti-bonding. So equal contribution in this case, equally होगा change. And so the electron distribution of electron cloud is identical when the two atoms are same, right, having same electronegativity. Okay, so electron distribution on this side, so everything was perfect. And this is transforming to this thing, antibonding MO. When you have asymmetric, the energy of orbitals are not same, the mixing is not, so we were trying to show that this is having greater contribution, which is less electronegative. So carbon is less electronegative, having greater contribution to the antibonding orbital. That is clearly shown in this, because drawing smaller lobes. This, ठीक है, ये चीज ध्यान देने वाली बात है. So we can clearly see in these pictures that what let me just get it clear, rub it. Okay, so what we are trying to show here, that this is the bonding MO, this one less electron density on carbon, more on oxygen, right? When we are talking about the anti-bonding, so this was pi in terms of pi and pi star. Here carbon more electron density. So we draw the lobes of the orbital bigger, where we have to show higher electron density. We draw smaller lobes of the orbital where the electron density would be less. Okay. Okay. So this is the contrast that you should observe in the two pictures. ये पिक्चर्स बुक में दिया हुआ है जेम्स हुई में, लेकिन आपको उसमें बैठ के समय देना पड़ेगा समझने के लिए. यू नीड टू अंडरस्टैंड, टू ग्रास्प व्हाट इट इज ट्राइंग टू कन्वे, राइट. सो वही मैंने आपका काम आसान कर दिया. And the same, so what we learned about this CEO, similar thing happens for this is for nitrogen and oxygen combination, and similar thing happens where you have this, or rather what I have said earlier, I will stick to it, that these orbitals are getting affected in energy. Sigma orbitals, which are having electron densities along the internuclear axis, they are getting affected. Pi orbitals is not affected for this. So from the model that we have just shown, and yeah, there one more thing with NO, that yeah, in a free molecule, it is the arrangement in a free. This is when free NO molecule, that is in a gaseous state. This is the kind of diagram, but when it is in the, if there is some kind of in a crystal, where we have electric fields from various type of sources, metal cations and others, ligand field, In a crystalline field, this will change to again p star. So this is the change that occurs here. Observe that pi was having the energy was here, and the energies show a slight shift. In this case, sigma again. So sigma का energy वापस change हो जा रहा है when there is electric field interaction. So this is two things happens. Then yeah, in the scheme of when we were discussing diatomic atoms, sorry, diatomic molecules. In that context, it is also becomes important. Although this will we will discuss it again in case of when we go to coordination, metal bonding, metal clusters. In that, there is a typical there is sigma when in there's let me just so in metal clusters typically in it happens in transition metals. Transition metal, when you have cluster of atoms combining together, in the metal clusters you will find there is sigma bond possibility of, so there is one along the internuclear axis combination of orbital dz square, and there's sideways overlap which can happen for dxz dy, which are lying uh, dxz d. Hello. Okay. किसी का माइक ऑन है क्या? मुझे दिख नहीं रहा है. ओके, सो ये थोड़ा सा आपको विजुलाइज करना होगा बहुत ध्यान से. Z square, when the two metal atoms are coming close to each other, d orbitals, dz square orbital is the first, so that the two atoms can combine. ठीक है? So there will be overlap of dz square. इसमें आप जाने ये plus minus, these two colors are to indicate two different sign of the wave functions. ठीक है? Negative sign of the wave function, positive sign of the wave function. So positive sign of the wave function, these two, so approaching in this direction, they will combine to have a constructive interference of the waves along the internuclear axis, and then having that z component along them, जो भी दो ऑर्बिटल हैं xz yz, इन दोनों का sideways there will be, this is the sideways overlap that can happen between these two orbitals xz dyz dyz. दिख रहा है? अगर ये z वाला एक्सिस है तो एक आपका x एक्सिस डिफाइन किया हुआ ना, x y z, सो अकॉर्डिंगली यू हैव x एंड y एक्सिस. सो ये प्लेन से बाहर निकल रहा है, आउट ऑफ द कमिंग आउट ऑफ द प्लेन ऑफ द स्क्रीन, दिस वन. ओके, कैन यू विजुअलाइज दिस? दिस इज इन द प्लेन ऑफ स्क्रीन x z. Okay, and this one is out of the screen, the two lobes are coming out of the screen, and this is the xy plane which is perpendicular to this screen. So ये जो है, this last one which is called delta bonds, these are face to face overlap. Overlap of the orbitals. इससे आपका, so there is possibility of 1 sigma 2 pi bonds, and there are two more orbitals left that will So you can get two delta bonds. So between two metal atoms there is possibility of 5 bonds that can be formed. दो एटम के बीच में ये आपको यूनिक पॉसिबिलिटी यहाँ पे मिलती है। अभी तक आपने ट्रिपल बॉन्ड तक देखा था कि कार्बन और बाकी सब में नाइट्रोजन में होता है, लेकिन यहाँ पे आपको 5 अप टू 5 बॉन्ड्स दैट कैन बी फॉर्म्ड dxy square x square minus y square. So to understand it better, so this is your axis sigma bond. कौन है? कोई है उसमें? मैं इसमें करूंगा तो फिर मेरा पूरा सेटअप गड़बड़ा जाएगा, फिर मुझे एग्जिट करना पड़ जाता है। ओके, सो जो हम ये तो इंटरन्यूक्लियर एक्सिस के अलोंग है, मेटल अलोंग द इंटरन्यूक्लियर एक्सिस, ये आपका सिग्मा बॉन्ड हो गया। दूसरा जो कह रहे थे पाई, ये हुआ साइडवेज ओवरलैप ऑर्बिटल्स। So this is your sideways overlap. Two orbitals having the lobes in this plane. So this is sideways overlap. ठीक है, ये sideways overlap हो गया, ठीक है, ऐसे करके। And now just bringing इस plane में जो ये z axis था, इसके perpendicular जो plane होगा वो xy होगा, उसमें दोनों orbitals होंगे, उनका face to face overlap. So the orbitals which are having x and y components, they will have this kind of interaction. Z का Z component रखते हुए तीन, you are having 3 orbitals with Z component, dz square dx क्या? अच्छा, प्रियंका, प्रियंका, can you mute yourself? Your mic is on, so that we can hear loud, creating disturbance. प्रियंका, हाँ ठीक है। तो फेस टू फेस ओवरलैप जो देख लें, ये डॉटेड लाइंस दिखा रहे, सो जो प्लेन परपेंडिकुलर ऐसे आ रहा है, मतलब एक एक्स जेड एक्सिस हो गया, डिफाइन कर दिया आपने, और इसके पहले वाले जो ऑर्बिटल्स थे, सो व्हाट यू वाज सीइंग हियर, दिस वाज dz स्क्वायर ठीक है, एंड दिस वर हैविंग बाकी दो ऑर्बिटल जिसमें z कंपोनेंट है, xz xz yz dyz d, ठीक है। दो ऑर्बिटल और बच गए जिसमें कि z कंपोनेंट z वाला नहीं होगा, वो पूरा उसके परपेंडिकुलर, उसका it will be lying perpendicular to the internuclear axis and they will having overlapping like this. So एक तो इंटरन्यूक्लियर एक्सिस के अलावा हो गया पहला dz स्क्वायर, दूसरा ऐसे है ना, और तीसरा ऐसे, 3 modes of combinations that you will, so just try to visualize that thing. Okay, so this is called face to face overlap. This is your face to face. So this particular mode of so in delta bond formation, this we know as delta bonds or delta orbitals, just as you have sigma and pi. So the example is here. If you can make the energy level diagram combining all the orbitals, you can make something like this. So you can see here, this is example of dibenzene chromium. So if you have benzene ring, benzene with some other aryl groups further, or they may not be hydrogen or maybe hydrogen, that can happen. So in this case 1 2 3 4 5, so maximum क्या? तो इसमें सिग्मा पाई, दो पाई बॉन्ड, सो टू पाई ऑर्बिटल बॉन्डिंग ऑर्बिटल, पाई एंटी बॉन्डिंग, ठीक है। टू डेल्टा ऑर्बिटल्स बॉन्डिंग, डेल्टा एंटी बॉन्डिंग, right? So this kind of scheme you can make up for so chromium here, look at this, dz square giving you this orbital, pi due to the combination of xz yz, and delta due to combination of these orbitals. So हाँ, ठीक है। सो ये एग्जांपल किया गया है, ये दूसरा एग्जांपल, दिस इज अनदर एग्जांपल ऑफ क्रोमस एसिटेट, द फोर बॉन्ड्स, चार बॉन्ड इसमें चार है। वो वो एक अलग एग्जांपल था। ये व्हाट इज दिस, दिस इज योर क्रोमस एसिटेट, व्हाट यू आर सीइंग हियर, ये दो क्रोमियम है, एंड दिस इज सी ओ ओ। So this kind of ligands, so this kind of bonding, so typically you will find this quadruple, so सिंगल, हाँ ये सिंगल डबल ट्रिपल, जब चार बॉन्ड होगा तो क्या बोलेंगे, क्वाड्रुपल, वन सिंगल, टू डबल, थ्री ट्रिपल, फोर क्वाड्रुपल, फाइव quintuple, so double bond, triple bond, quadruple bond, and quintuple bond। ये मतलब नाम अगर हम देते हैं तो इस तरह से कि पांच बॉन्ड बन गया। तो पहले वाला जो एग्जांपल था इसमें पांच था, दिस वाज एग्जांपल ऑफ हैविंग क्विंटुपल बॉन्ड, दिस वाज एग्जांपल ऑफ क्विंटुपल बॉन्ड, ठीक है। दो एटम के बीच में मैक्सिमम मैक्सिमम जो बॉन्ड हो सकता है वो ये हो सकता है, फाइव। Quadruple, so and this is example of chromous acetate, this is the acetic acid as a ligand, when you take that, this is it happens like this, and we have so these are, so in case of rhenium atoms, again rhenium chloride, so four bonds you can see, so there is only one delta bond that is formed, two pi bonds, so they are the weakest, so that is delta bonds represent the weakest form of overlap between two orbitals, okay. So sigma pi, and just representation of the same thing, how they we can consider them to be overlapping with each other. So z axis xz, and then dxy, so this is these are the schemes that you can draw for, so I have okay, so I think we can so we have reached a stage where we can we have discussed every aspect of two bonds formed between two atoms, diatomic bond theory, ठीक है। Now we can move from 2 to 3 triatomic molecules. We can take a 5 minutes break here.